Hi, I'm Dupree, and I'm going to be talking to you all about how to heat treat metals and how it relates to thermodynamics. So to start off, what is heat treating and why do we do it? It's basically just controlling the temperature of a metal to leverage a certain mechanical property through altering its microstructure, whether it be the grain itself or the number of grains. You can see, for example, these are two different versions of precipitates on the bottom left. We'll talk about those more at the end. And then on y'all's right side, those are examples of carbon steel grains, such as cementite, ferrite, and perlite and stuff. If you're going to heat treat a metal, you need a certain type of equipment. For one thing, you can just weld it, but that's usually an inadvertent, undesired effect, the heat treating. If you're treating a metal to prepare it for use, otherwise you need an oven, typically some tongs, gloves, a crucible, and possibly a cool bath if you're going to quench it. So here's an example of a phase graph that we've all seen before. On the bottom we have a ratio of one element to another. So these numbers are the percentage of aluminum, their percentage of copper, and the rest of it is aluminum by weight. And you see we have various zones of the graph. Alpha is one type of phase, theta is another, L is another. And all this shows is that with everything else held constant, if you raise a alloy of this much copper to this temperature, you're going to get pure alpha phase. Or if you bring it over here, you're going to get some combination of alpha and theta. And depending on the exact temperature and ratio, you're going to get a certain amount of theta to alpha phase, and same for the alpha to theta and so on. So there's three main different ways for heat treating metals. You can anneal it, you can solid solution strength it, or you can get precipitation hardening. What annealing does is that it puts in energy in the form of heat to allow the atoms to diffuse and create a continuous matrix. Solid solution strengthening is your basic alloying method. You're just putting in an evenly distributed amount of different element to leverage those properties, which are basically dependent on the size and the electron cloud of the elements. And then you have precipitation hardening, which is a little more complicated. You're typically trying to develop Guinea-Preston zones. And it's more complicated because you're cycling heating instead of just heating it once and cooling it or not cooling it actively. And we'll talk about these three a little more. So first, annealing. This is typically used to increase ductility at the cost of strength. And like I said, the purpose of annealing is to add heat to allow the atoms to diffuse, because normally in nature things want to be evenly distributed. By adding that heat, you're taking out the work, aka the strain, within the metal. And it's usually designated with a hyphen O at the end, so if you see something like aluminum 7025-O, that means it's annealed. So you would immediately see, oh, that's a ductile metal. I want a stronger metal, so you wouldn't go for the one with the O at the end. And then you also have the optional step of refining the grain after annealing it, which is quenching it. You can put it in a cold bath to quickly cool the metal, which results in a smaller grain size, more grains within the same area. And more grains means more planes for these grains to interact, which means it's stronger material, fewer planes to slip. So if you quench it, you're going to get something a little harder. Otherwise, you'll get a relatively ductile metal. And the second one, solid solution strengthening, that's your typical alloying method. You can either have an interstitial or a substitutional alloy. The interstitial one is what you get when you use a pretty small element relative to the matrix element. In either scenario, you're distorting or straining the crystal lattice, and therefore making it stronger, harder to slip. There's an asterisk there because if you keep on adding solid, it'll get stronger up until a certain point when you're making more of one element than you are an alloy. And then lastly, precipitation hardening. So when you solution heat treat something, you are creating a supersaturated solution. And what that means is it's unstable. You can do afterwards is you can quench it, and that keeps it in the unstable state. And it will mostly retain that microstructure, but it'll kind of degrade over time a little bit, exponentially so. Instead of quenching, what you can do is age it, either naturally or artificially, and that will allow some of these Guinea-Preston zones or the precipitates to coagulate and stay together. Also, notice the difference between these two is you're getting a supersaturated solution with the quenching versus getting a two-phase mixture where you're getting two distinct elements. So when you age it and you get this two-phase mixture, you can either allow the Guinea-Preston zones to develop so much that you get something that's incoherent or not continuous with the matrix's crystal lattice, and that's more of a disruption, so it's stronger than this, a coherent precipitate or Guinea-Preston zone. So in conclusion, you heat treat metals by putting in heat and timing it in the amount of temperature to leverage certain mechanical properties such as elasticity, strength, and ductility. Any questions?
So in all the three processes you mentioned quenching. You pretty much do quenching in all the three.
Yeah.
Can you explain what happens in quenching?
What you're doing is you're cooling the metal rapidly enough to not allow the crystals to realign with each other. So since they're not realigned when they cool, you end up with boundaries, which is how you get grains, where different lattices have different orientations. More grains, typically stronger.